Hi all, welcome to CircuitSutra's video demonstration on CST board Zinc. This demonstration is about CST board Zinc, an extendable virtual platform of Xilinx Zinc 7000. This virtual prototype is developed using CST Chemo, System C and TLM 2.0. Before jumping into the demonstration, I would like to give you some overview on Xilinx Zinc 7000 and its reference VP available in Chemo. Xilinx Zinc 7000 is a FPGA SoC from Xilinx. It have a fixed SoC and the FPGA portion in which additional designs can be implemented. The fixed SoC portion also allows to configure what all IPs are to be connected at what address space. This chip provides the best of both worlds, a generic SoC and the field programmability of FPGA. In Chemo, there is a reference board for Xilinx Zinc 7000. This virtual platform is implemented by Xilinx and is capable to boot Linux. It represents the virtual model of fixed SoC portion of Zinc 7000. Address space and IP connections of this board are configurable through a device tree source or .dtsi file, which is compiled to a .dtb or blob file and provided while bringing up the board. The reference board shown in the previous slide is extended using CircuitSutra CST Chemo. This allows to integrate the System C models of additional IP. This gives us extendable virtual platform of Xilinx Zinc 7000. The virtual platform have two portions. The fixed SoC portion is represented by the model inside the Chemo. The design IP that needs to go into the FPGA portion can be modeled using System C or TLM 2.0 and connected at vacant address spaces. Such a setup provides a very powerful development environment to the users of Xilinx Zinc 7000. They can use this virtual platform for the device driver or firmware development for the additional design IP that goes in FPGA portion or for the embedded application development for the entire system. It also enables the powerful automated unit testing of firmware or embedded software. For the demo purpose, we have connected the System C or TLM models of a UART and a memory. We will demonstrate how to effectively use this VP. Nowadays, high-level synthesis-based design flows are becoming popular in FPGA community. This allows the users to implement the designs in System C instead of implementing in Verilog. Such HLS design implementation model can also be connected in this virtual platform and be verified in the entire SoC through bare metal tests, etc. Let's start the demo. First in the list is instruction tracing. Before jumping into the actual demo to show about the instruction tracing, I want to touch upon few basic things to set up and invoke VP. This is the cst setup.sh file where one has to provide the required environment variables and source the same to get reflected in the terminal window. Currently, this file is already sourced and ready to invoke the VP. This is the config file. .lua contains hierarchical list of configuration parameters and is passed while invoking the VP. One can set parameters either for the entire VP or for the individual IP models. For example, here we have set a log level of 3 for UART model. During my slide presentation, recall I discussed about two portions, namely fixed, which in this case is Zinc 7000, and a configurable or System C portion of SoC. We are instantiating them here in main.cpp. This is the .dtsi or device tree source file provided by Xilinx for Zinc 7000 reference board. This contains details about instances of CPU models, Chemo, IP models, and their registration at corresponding address spaces, interconnections between them, etc. This forms the fixed SoC portion. This file cst board zinc.cpp contains details about the configurable or System C part of the SoC. Here, memory and UART are instantiated and registered with sysbus at available vacant address spaces, which are found from the above.dtsi file. VP can be invoked using cstboard.exe and there is a small help menu to assist with. Let's get started with instruction tracing. In this example, we have a small assembly code. We will execute it on VP using -trace option and will generate the instruction trace. As you see, this code has simple ARM instruction and branch instruction in it. This is the instruction trace file. This trace file contains the instruction type, which could be one of the four. IT means instruction taken, IS means instruction skipped, BT branch taken, BN branch not taken, followed by address, opcode of the instruction. Updated register values from R0 to R15 are dumped along with the above details. Moving on to the next in the list of demos, that is embedded software logs via semi-hosting. In this example, we demonstrate the semi-hosting feature to print the debug messages from embedded software. As we all know, the most common method for debugging any software is to print the log messages from different part of the code. The embedded software engineers generally use the hardware boards or real embedded product to run and test their software. Hence, they are not able to use this powerful debug method. However, if you use virtual prototype, then you may print the messages from the embedded software code on the terminal window or the log file on the host computer. For achieving this functionality, VP uses the semi-hosting feature, which allows to use the input-output resources of the host computer in the VP. In this example, we have an assembly code which prints a debug message from assembly program. Here, QEMU uses SVC instruction with a specific literal value 0x123456 to invoke the semi-hosting. Let me run this program. One can see the debug messages printed onto the host console. Next in the demo is hardware logs. Another important feature of virtual platform is that the debug or information messages can be printed from within the hardware as well. From these messages, you may judge what specific functionality of the hardware IP was invoked, what was the state of the specific register or buffer or signal, etc. The hardware logs, along with embedded software logs, provide very powerful debug setup and can be quite useful to debug the corner case scenarios. In this demo setup, the models are developed using CircuitSutra modeling methodology. By setting different value of log level in the lower config file, user may activate different kinds of logs or information messages being printed. We are setting a log level of 3 for UART model. Here is an example code where we push few characters into UART data register and also configure few UART registers to generate interrupt. One can see the UART logs printed onto the console. Next, we move on to automated unit testing of firmware. The three features we have seen so far, instruction tracing, embedded software logs and hardware logs, play a vital role for creating an automated unit test case. A typical unit test case will start with a small C or assembly code, cross-compile using toolchain, run it on the VP, generate trace or log files, compare with golden files to decide a pass file. A top-level script may be developed to run thousands of such unit test case. Here is an example of one such setup. This is a sample regression script which deletes a previous results, back up the config file, disable the CST terminal, clean the previous log files and binary files, build the test case, invoke the VP, enable the logs, load the binary and run. Once the log files are generated, assess the results based on the logs, and once all the test cases are run, restore the original config file and print a summary. This is a very simple setup created for demo. A more comprehensive setup may be created to monitor various quality parameters like coverage, memory, profiling, etc. Nowadays, as the amount of embedded software that runs on SoC is exploding, this huge embedded code have to be maintained, enhanced throughout the life cycle of the product. Hence, you need to have right process in place that allows you to monitor, maintain the quality of the embedded software. Automated unit test suite can be part of your nightly regressions too. A summary is also dumped into results.out. One can go into individual folders to find out the logs to debug and analyze. Next in the list is software debugging using ARM-GDB, which is a common scenario during development phase of a software. In addition to debugging embedded software, here one also co-debug software with hardware and also inject errors in hardware, which is almost impossible to achieve in real hardware. Let us see how we can do this. I am going to invoke VP using gdb-args, and also in order to debug the embedded software I am going to use these two options. -s is to start the GDB server in VP and -S is to freeze the CPU at the start. Using .gdb init file, I have already applied a breakpoint to the UART data register's post callback function. Now the VP is up. Let me invoke the embedded software GDB, which is ARM-GDB here. I am connecting to the target, which is listening at port number 1234. Okay, this is the function where we are pushing some characters into the UART data register. If you see, the first letter H is assigned to star S or the pointer value. I can change this to any other character in the embedded software and run. So when it has been pushed into the UART data register, the control goes to the VP. Here the UART data register's post callback function is called with the data value 86 or V. Since this data type is a constant data type, I will not be able to change it here, so I am moving to a function where I can change this. Here I am changing this to W. And continue further. So if you see in the embedded debugger, the value H has been changed to V, and in the VP the value V has been changed to W, which is reflecting in the CST terminal, which is connected at the back end of the UART. So this is a simple example to show how to inject errors in VP. Similarly, one can also inject errors in signals, control events, etc. and observe the response of the VP or hardware for corner cases, which could be rare or occasionally occurring in real hardware. Last item in the demo is booting Linux. The command to boot Linux is this. You need to pass the kernel, DTB image and the initrd image. A small kernel module which maps the UART register space and pushes some characters to UART data registers is being compiled so that once installed onto the Linux, it can access the UART and push some data characters. Linux is booting up. The particular test module is already compiled here. On installing this test module, you get the messages from the UART and it displays in the CST terminal. Likewise, basic embedded software development, debug and testing is feasible with this setup. For advanced hardware level debug analysis, we recommend to use virtual prototyping tool. That ends the demonstration. Thanks for watching.